in this lecture, we will first talk about something called steady state, okay, during heat conduction. And after that, we'll solve problems based on conduction. Okay, consider an object like this. You can think of it as a rod or a metal strip. Okay, let's say the object is initially at room temperature. The entire object is at the same temperature. Okay, so if the temperature is same everywhere, you can call it as uniform temperature. Okay, remember there is a meaning to this term uniform. Uniform means being same everywhere in space. Okay, means being same at all points. So if the temperature is uniform, that we mean to say that temperature at every point of the object is the same. Fine. Suppose you start heating this object. Okay, at one end you start heating it. At the other end, let's say you put it in uh, ice, melting ice. Okay. Sohan, quickly tell me what is the temperature of melting ice?
0 degrees.
0 degrees. Okay. Until all the ice melts into water, the temperature will remain zero. Okay. So on one side, let's say there is melting ice. At the other end, let's say you are heating it. Okay. So you just started this process. Fine. So at the beginning, when you just put melting ice on one side and start heating on the other side, temperature will still be uniform. Okay. We just started trying to change the temperature. As of now, the temperature is same everywhere. Okay. So Sohan, tell me, based on your everyday experience, what is going to happen to this rod in terms of temperature? Will the temperature still remain same everywhere, or will you see temperature changes happening?
So non-uniform temperature change will take place.
Okay, it will become non-uniform, you are saying. Fine. We assume the object was initially at room temperature. Let's say room temperature is 25 degrees C. So temperature everywhere in this object is 25 degrees C initially. Okay. Now, when you put flame on one side and melting ice on the other side, melting ice is at 0 degrees. Let's say the flame is at some high temperature, maybe 300 degrees C. Okay, it cannot be 300 degrees C, but anyway, flame after passing by some distance can come down to that temperature. Let's assume something like this. So we are keeping one end of this rod at 300 degrees, the other end at 0 degrees. Initially, the entire rod was at 25 degrees C. So now what will happen? The end which is in contact with the flame, okay, its temperature will tend to rise. Okay, this end's temperature has to rise. The end which is in contact with ice, its temperature has to fall. Okay, because ice is at 0 degrees. Originally, the end was at 25 degrees. So one side the temperature is rising, the other side temperature is falling. Okay. So what will happen, as you said, okay, what you said is correct only. There will be a non-uniform temperature developed across the rod now. Okay. Uh, but see, temperature changes will take time to happen. Initially, the entire rod was at 25 degrees. Now, on one side, we are rising the temperature, the other side, we are decreasing the temperature. Okay. So, what will happen in a short while? You will observe something like this. There will be a temperature gradient. What does gradient mean? If any quantity varies from point to point, okay, you say there is a gradient of that quantity. Just a moment. So as you start heating one end and cooling the other end, you will see a temperature difference appearing across the rod. Okay. Now you are continuing like flame we assumed is at 300 degrees C, melting ice is at 0 degrees C. So the temperature of this end continues to rise. and the temperature of the other end continues to fall. So there will be a temperature gradient developed now. Okay. Now the left end, its temperature will go on increasing till it reaches 300 degrees. The right end, its temperature will go on decreasing till it becomes 0 degrees. Okay. But that will take time to happen. Originally, the entire rod was at 25 degrees. No, immediately the left end will not go up to 300 degrees. It will take a short while. Okay. Because as the molecules receive heat, they'll be passing it also. Okay. So their temperature won't immediately rise to 300. It will take some time. So after some time, the situation will be like this. After some more time, okay, the temperature of the left end would have increased a little further. Okay. Maybe in this situation, okay, like in the second diagram, maybe the temperature is some 80 degrees C now. Okay. Right end, maybe the temperature is some from 25, it is decreasing. No? So maybe it is some 15 degrees C. Okay. They will still change. Okay. So as you continue heating the left end and cooling the right end, temperatures will change further. So left end maybe goes to a temperature now like 200 degrees C, but flame is at 300 degrees C. So the temperature will still continue rising. Okay, it has increased, it has to increase further also. Right end, let's say the temperature has now come down to some maybe 5 degrees C. Okay, but ice is at 0 degrees C. So it has to fall a little further also. Okay. Now we can't say like both ends will come to stable temperature at the same time. Who knows? The right end may come down to 0 degrees before the left end goes to 300 degrees also. Okay. Those things we will not be bothered about right now, but temperature changes will happen. Okay. And after some more time, or if you give it sufficient amount of time, you will see the temperatures stabilizing like this. The left end will finally attain a temperature of 300 degrees. Okay. You continue, you continue the flame, and let's say the ice has still not melted. So right end continues to be at 0 degrees, and the end has actually reached a temperature of 0 degrees. The flame is at 300 degrees. Let's say this end has actually attained a temperature 300 degrees. Okay. Now no further change in temperature will happen. Okay. Now one end is at 300, the other end is at 0. That naturally means that other layers in between will be at temperatures between 300 and 0. You will find one layer of molecules here which may be at a temperature of 200 degrees C. Okay. You will find another layer of molecules here which may be at a temperature of 100 degrees C. So there will be a temperature gradient developed across this object. Okay. So observe what happened. Initially, the entire object was at 25 degrees. When we put ice on one side and flame on the other side, the temperature started to change. Okay. Time to time they were changing, and place to place also they were varying. Okay. Originally it was uniform, means it was same everywhere. But once you start heating one end and cooling the other end, or even if you just heat one end, that's enough, or cool one end, that's enough, the temperature becomes non-uniform. And see, it has not attained steady temperature also. Left end, we are trying to bring it to 300 degrees. It has not come to 300 degrees yet. So it is changing time to time also. So it is non-uniform and also non-constant. Uniform is with respect to space, means point to point. Point to point, if there's a variation in temperature, you say it is non-uniform. Constant is with respect to time. So time to time, if it is changing, then you say it is non-constant. Fine. So as the temperature is increasing on one end and decreasing at the other end, it's both non-uniform and non-constant. Okay. Next, after some more time, we assume left hand comes to 200, right hand comes to 5 degrees. It's definitely non-uniform, and the temperatures have still not reached the stable values. So it's still non-constant as well. Okay. Finally, when left hand comes to 300 degrees and right hand is at 0 degrees, no further change in temperature will happen here. No further change will happen here also, and no further change will happen anywhere in between also. Okay. Then you can say that temperatures are still non-uniform. Okay. But now they have become constant. They won't change anymore. Okay. Every point's temperature is now fixed. Point to point, it may vary. For a particular point, it is fixed now. Okay. This is what we call as steady state. When this happens, we say that steady state is established. And the equation that we discussed in the last class for rate of heat transfer through conduction, dq by dt is equal to Ka delta T divided by L. This is valid only under steady state condition. Valid only after steady state is established. Okay, it is very important to remember the conditions. We had discussed few more conditions also in the last class itself. This is valid only if conductivity is uniform, area of cross section is uniform, all those things. Now we are adding another condition. This is valid only if steady state is established. Okay, and in your syllabus you only have those questions where steady state has already been established. Okay, now let us discuss a little further about steady state. Now you consider any layer of molecules. Let's say this layer which is at 200 degrees C. Okay, its temperature has become steady now, means constant. Now on the left side, the rod is at 300 degrees. At the right end, the rod is at 0 degrees. So definitely transfer of heat will happen. Okay, from higher temperature to lower temperature, heat transfer will definitely occur. But a particular layer's temperature is now constant. What does that mean? Does that mean there is no heat being received by that layer? It will definitely receive. Okay, there will be heat transfer happening from the left end to the right end. Okay, even after steady state is established. Heat transfer is going on. So if you take any particular layer, it does receive heat from the left side, but it also releases heat to the right side. Okay, heat passes through the layer, that's all. And since the layers have attained a steady temperature, a constant temperature, we can tell for sure that the heat received by the layer in a certain amount of time is equal to the heat released by it. Means inflow of heat should be equal to outflow of heat. That is what we call as steady state. Okay. Therefore, at steady state, rate of inflow of heat to any layer of molecules is equal to or must be equal to rate of outflow of heat from that layer. Okay. So based on this, we'll be able to write mathematical equations as well once we know that steady state has been established. Fine. Uh, in fluid mechanics also, we had a concept like this. If the fluid is incompressible, rate of inflow is equal to rate of outflow. It's called equation of continuity. Okay. So writing equation of continuity for heat flow, we can solve problems based on conduction. Okay. Now, rate of heat flow through conduction, we have this equation, right? So you can write rate of inflow using this equation. You can write rate of outflow also. Equate them. You'll be able to solve problems. Fine. So let's take this example itself. Let's say one end is maintained at 300 degrees, another end is maintained at 0 degrees. Okay, steady state is established. Unless otherwise specified, you assume steady state has been established. Okay. So temperatures are non-uniform, but they have now become constant. So there is definitely heat transfer happening. You know the temperatures. Let's say the length of this rod is some 2 meters. Cross-sectional area, let's say, is 10 square centimeters. Conductivity we need to give. Just a moment, I'll look up some practical values of thermal conductivity. So let's say the thermal conductivity of this material is 50 watts per meter per Kelvin. Okay. So now that you know K, A, and L and the temperature difference as well, you should be able to find out first the heat current through the rod. Heat current is nothing but dq by dt or delta q by delta t. Okay. Calculate this quickly, both of you. Okay. Steady state has been established. There is only one path for heat flow. It's a very simple question. Direct application of the formula Ka delta T by L. Okay. K is given in SI units, so you can substitute it as it is. Cross-sectional area 10 centimeter square. This is not in SI units. So in SI units, it becomes 10 into centimeter is 10 power minus 2 meters. When you square it, it becomes 10 power minus 4 meters square. Next is the temperature difference between the 2 points between which you want to find out heat current. Okay, 300 0 temperature difference is 300 units. Okay, difference in temperature will be same in Kelvin units as well as Celsius units. So you can write 300 directly divided by the distance through which heat has to pass, 2 meters. Simple. So 10 power minus 4 and 4 zeros can be cancelled. 5 threes is 15 by 2 is 7.5. So 7.5 watts is the heat current or 7.5 joules per second. Aishwarya, is this clear? Any doubt? No response. Fine. Okay. Now we found out the heat current through this rod. That is the rate at which heat flows from one end to the other end. Okay. We took the complete length. 7.5 joules per second is being passed from end A to the end B. That's okay. Now you consider a random section in between. Okay. Random cross section somewhere here. Now if 7.5 joules per second is passing from A to B, that means through every layer of molecules, there will be a heat of 7.5 joules passing per second. Okay. From one end to the other end, the effective heat current is 7.5 joule per second, means everywhere the current is 7.5 joule per second itself. That means this layer will be receiving a heat of 7.5 joules every second, and it will also be releasing a heat of 7.5 joules every second. That is what will happen, because only then you can have an effective transfer of 7.5 joules per second from one end to the other end. Okay. So what this means is, if you know the heat current for the entire rod, that means you know heat current everywhere. It's the same, it has to be the same everywhere because there's only one rod here. So if you consider some other section, let's say call this layer as C, then the current from A to C should be equal to the current from C to B, and that should be equal to the overall current. Okay. So once you know the overall heat current through a rod or an object, you can tell the heat current between any 2 points also. Fine. And if you know that heat current between any 2 points, you can tell the temperature difference between those 2 points. That means you can estimate the temperature of C, any section in between. Let us do that now. Consider this same situation. You know the heat current is 7.5 joules per second. Okay. One end temperature is 300, the other end temperature is 0 degrees. Okay. Now, somewhere in between, the temperature of a layer will be 200 degrees. Okay. Find out where that temperature will be observed. Means you have to find out this distance where the temperature will be 200 degrees C. Okay, let me give you those values once again. Conductivity, thermal conductivity is 50 watts per meter per Kelvin. Length of the total rod is given as 2 meters. And cross-sectional area was given as 10 centimeters square. I want you to find out the distance from the left end where the temperature is 200 degrees C. Okay, at steady state. Try this, all of you. Okay, I got one answer as 2 by 3 meters. Fine. Sohan, can you tell how you arrived at that answer?
Sir, I equated the heat currents.
Okay, fine. Since steady state is established, heat current everywhere should be the same. Between any 2 points, the heat current should be the same because there's only one rod here. Fine. We know the heat current is 7.5 joule per second. So just write 7.5 is equal to K A delta T. That becomes 300 minus the temperature at that section is 200 divided by the distance. Distance is unknown. That's all. From there, you will get the answer. Fine. Let's consider one more case also. Let us generalize this. Suppose there is a rod of uniform cross section, uniform conductivity. Steady state has been established. Okay. Let's say temperature at one end is T1. It is maintained constant. Temperature at the other end is T2. It is also maintained constant. Okay. By some means, we are maintaining them at constant temperatures. And let's say the total length is L, conductivity is K, area of cross section is A. So you can easily tell what is the net rate of heat transfer or the effective rate of heat transfer. What I want you to find out is at a random distance x from the end which is at higher temperature. Okay, let's assume T1 is more than T2. So at a random distance x, derive the expression for temperature. Okay, so x is also given to you. You have to derive the expression for temperature there. Try this. I'll give you 2 minutes. Right. The idea here is the same. The net rate of heat transfer through the entire rod would be equal to the rate of heat transfer between any 2 points of the rod. Okay. So dq by dt, once steady state is established through the entire rod, you can say it is Ka. Temperature difference will be written as T1 minus T2 divided by L. I am assuming heat transfer from left side to the right side. Okay. In that direction, heat current will be written this way. We'll discuss this a little later. And this should be equal to rate of heat transfer between these 2 points. You can call them as X and Y. Then you can write it as Ka. Temperature difference between X and Y is T1 minus T. T1 is the higher temperature, T is the lower temperature, divided by the distance between them is X. So K and A will get cancelled. That's all. You can find out the temperature now. So you can say T1 minus T2 multiplied with X by L is equal to T1 minus T. Or you can look at it this way also. T1 minus T2 divided by L is equal to T1 minus T divided by X. This way it is easier to remember and understand also. T1 minus T2 is the total temperature difference across the length L. Okay. So this is total temperature difference. L is total length. What do you have on the right hand side? Partial temperature difference. And this is partial length. So basically, temperature difference divided by the distance is same everywhere. Okay. And temperature difference divided by distance between 2 points is nothing but temperature gradient. Generally, gradient of any quantity y is change in y per unit change in distance x. Okay. You call this as gradient. Fine. Now, what you see from the result here is that T1 minus T2 divided by the distance between those 2 points is equal to T1 minus T divided by the distance between those 2 points. So what this effectively means is at steady state, okay, provided some conditions are satisfied, conductivity should be same everywhere, area of cross section should be same everywhere. Because while deriving this, we cancelled K and A. Only if they are same everywhere, they can be cancelled. Okay. So at steady state, under uniform conductivity and cross-sectional area, the temperature gradient is uniform. Means difference in temperatures of 2 points divided by distance between those 2 points will be same for any 2 points of the rod. Okay, using that you can tell the temperature anywhere. Okay, let us use this idea to solve the previous question now. Okay, previous question how we solved was we already determined the rate of heat flow. Based on rate of heat flow, we got the distance x. Okay, but let's now use this idea. If you apply that, see, we know one end is at 300, the other end is at 0, and total distance was 2 meters. Okay, so how do you write temperature gradient? 300 minus 0 divided by 2. Temperature difference divided by the distance between the points should be equal to the gradient across this part. Okay, what is the temperature difference between these 2 points? 300 minus 200 divided by what is the distance between those 2 points? X. That's all. 300 minus 200 is 100. Zeros cancel. You get x is equal to 2 by 3 meters. You could have easily solved the question this way also without finding out heat current at all. Okay, so remember, at steady state, if conductivity is uniform and area of cross section is uniform, temperature gradient will be same everywhere. Means difference in temperature divided by the distance between the points will be same for any 2 points of the rod. Okay, right. Now, yeah, the way we are writing heat current. Now, one end, let's say this end is at temperature T1, this end is at temperature T2. Assume T1 is more than T2. Now you know heat flows from higher temperature to lower temperature. So heat current is in this direction. Actual heat current is in this direction. Or actual heat flow is this way. Now, even though actual heat flow is in a particular direction, you can write an equation for rate of heat flow in any direction you want. Okay, what do I mean by this? Suppose actually there is 10 joules of heat flowing per second from left to right. Why will it flow from left to right? Because left end is at higher temperature. So let's say the actual rate of heat flow from left to right is 10 joules per second. You can also call it as minus 10 joules per second from right to left. You can write current like this also. Okay. So now see, in one direction it is plus 10, in another direction it is minus 10. That means the numerical value of heat current can change based on the direction in which you are writing the current, in which you are expressing the current. Okay. So suppose you want heat current towards right. How do you write the equation? K A delta T. Now heat current towards right has to be positive. Then you should do higher temperature minus lower temperature divided by the length. Okay. Suppose you want heat current towards left, or you want to express heat current towards left. Then you should write, I mean, the answer has to be negative. So you should write Ka T2 minus T1 divided by L. Only then you will get a negative answer. So the way we are writing the equation has changed depending on the direction in which you want the heat current. So generally, if you want to summarize this, you can say that heat current should be generally written as Ka, like based on the direction in which you are going, temperature at the initial point minus temperature at the final point. That is how you are supposed to write heat current depending on the direction in which you want the current. Now you observe both equations. If you want heat current towards right, initial temperature is T1, final temperature is T2. That is what we have written here. If you want heat current towards left, initial temperature is T2, final is T1, and that is what we have written here. So we can generally say that if you want heat current in a particular direction, you write it this way. Ka multiplied with initial temperature minus final temperature divided by L. Okay, means initial point temperature minus final point temperature divided by L. That way you will always get the correct result for heat current. Okay, let's make use of this point also in one problem. Suppose there is a junction of rods. Just a moment, I'll draw the diagram. Okay. Suppose there's a junction of rods like this. Yeah, as you can see, the rods have different areas of cross section. One is a very thick rod, one is moderately thick, the other is very thin. Their lengths also could be different, their materials also could be different. Okay, so let's say this rod's length is L, conductivity is K, and area of cross section is 4A. This rod's length is L, conductivity let it be 2K, area of cross section let it be 2A. And the third rod, it is longer, length let's assume it is 2L, conductivity let it be K itself, area of cross section is A. So there are three rods, different conductivities, lengths and all. Initially, let's say the entire system is at same temperature, but we maintain various temperatures at the ends of the rods. Okay, for example, let's say uh, this end, let it be maintained at 0 degrees C. Somehow we are maintaining it at that temperature. This end, let's maintain it at some 50 degrees C. And this end, let's say it is kept in boiling water, so its temperature will be maintained at 100 degrees. So heat transfers will happen, and finally steady state will be established. Okay. At steady state means once the temperatures become stabilized, what is the temperature of the junction? That is the question. Okay, lengths, conductivities, they are all given, and you are told that steady state has been established. Okay, so at a steady state, how much is the temperature of the junction? What does steady state mean? Inflow of temperature should be equal to outflow. Means temperature of a particular layer has become constant. So inflow should be equal to outflow. Now, see the temperature here could be like, look at the temperatures 100, 50, 0. Highest is 100, least is 0. So temperature here can be any value somewhere between 100 and 0. It may be 50, it may be less than 50, it may even be more than 50. Suppose this junction temperature is less than 50, let's say some 30 degrees. Then what will happen? Here there will be inflow. Here also there will be inflow, and here there will be outflow. Heat flows from high temperature to low temperature. That is one possibility. Suppose this junction temperature is some 60 degrees C. Then what will happen? Here there will be inflow, and in the other two there will be outflows. That possibility is also there. We don't know the temperature of the junction. It's also possible that the temperature of the junction is exactly 50 degrees. Then in this case, there will be inflow here, there will be outflow here, there will be no flow at all in the third rod because there's no temperature difference. So we don't know the exact direction of heat flow in one of the rods. Okay, we may not know the direction of heat flow in any rod also. Now, what does steady state mean? Inflow is equal to outflow. There is another way of looking at steady state also. Okay, inflow is equal to outflow. That's fine. You can write an equation on this basis. You can also say net inflow is equal to 0. Means you can assume inflow from all sides and equate that to 0. You can also say net outflow is equal to 0. Like recently in calorimetry, we solved some problems. We know that when objects of different temperatures are put together, heat lost by the hotter objects is equal to heat gained by the cooler ones. Now, if multiple objects are put together, we don't know which object is exactly going to gain heat and which object is exactly going to lose heat. Then in that case, what did we do? Net heat gain is equal to 0. We wrote the equation that way. Okay. Heat gained by the first object plus heat gained by the second object plus so on. Heat gained by the nth object. This sum should be 0. Okay. We are doing something similar here. If you don't know the direction of heat flow in one rod or some rods, then you can go this way. You can assume inflow in all the rods, write equation accordingly and equate it to 0. You can assume outflow in all the rods, write equation accordingly and equate it to 0. Or you can also assume inflow in some, outflow in some, and write inflow is equal to outflow. So which way you write the equation is your choice. Derive the temperature of the junction. Okay, try this both of you. Okay, listen. We have three different rods here. That's fine. Now, the area of cross section conductivity may vary from rod to rod, but in a given rod, the conductivity and area of cross section are uniform. So you can apply the formula that we have learned, Ka delta T by L, for heat transfer through each rod. Now, steady state has been established. At steady state, some junction temperature T will be there. Okay. Now I'll solve it in two of these methods. One method I'll write inflow is equal to outflow, but I'll have to make an assumption here. In the third rod, that 50-degree rod, we don't know whether inflow is going to happen or outflow is going to happen. So I will assume inflow happens. Okay. So let's say there is inflow in these two and there is outflow here. Okay. Now how do we write the equation? Net inflow is, I mean, total inflow should be equal to total outflow. Okay. This is where we need to be careful. This is where what we discussed just before will matter. You will write the equation based on the direction of flow that you are assuming. Now, inflow is equal to outflow, no? So if I want to write inflow, there are two rods in which inflow is happening. Let me copy this diagram just a moment. Okay. There are two rods in which inflow is happening. So we know the direction of flow. Then in that rod whose one end is maintained at 100 degrees, I should write K, conductivity is K, area of cross section is 4A. How to write delta T? Initial temperature minus final temperature. Okay, temperature at the first point minus temperature at the last point in the direction in which you are assuming the flow. I am assuming flow is from 100 degrees to T. So I should write 100 minus T divided by the length of that rod is L, plus there's another inflow that we have assumed. Conductivity is 2K, area of cross section is 2A, and based on the direction of flow, the first temperature is 50, final temperature is T, divided by the length is again L, should be equal to right hand side. We have to write outflow. Outflow is from T to 0. So I should write K, area of cross section is A, temperature difference is T minus 0, divided by the length is 2L. Okay. Now K, A and L can be cancelled throughout because they are common. You will be left with first part 100 minus 4 into 100 minus T, that is 400 minus 40, plus second part of the equation 2 into, okay, 2 into 2 is 4 into 50 minus T, that is 200 minus 40 is equal to T by 2. That's all. Solving this, we can get the answer for T. 400 plus 200 is 600. Minus 40 is minus 8T is equal to T by 2. Cross multiply, simplify. You get 1200 is equal to 8 to 16, 16 plus 1, 17T. So T becomes 1200 by 17. How much is that approximately? 70.59 degrees C. Okay, that is the junction temperature. And how did we derive this? By writing inflow is equal to outflow. I assumed two rods had inflows. One rod was giving outflow, and accordingly we got this answer. Now, see, I didn't know whether the junction temperature was going to be less than 50 or more than 50, but I assumed inflow in that 50-degree rod also. That's okay. The equation will take care of it. You write the equation properly, you will get the correct answer. Okay, let us solve this problem in another manner. Let's assume inflow in all three rods. Inflow here, and also inflow here. Then how should you write the equation? Net inflow is equal to 0. Okay. Then in that 100-degree part, just a moment, I'll have to copy the diagram once again. In the rod whose one end is maintained at 100 degree, okay, this time we want to write inflow in all three. So we are going to write total inflow is equal to 0. So K A delta T divided by L. That is inflow in the rod whose one end is maintained at 100. Next, 2K 2A delta T divided by L. That is inflow in the rod whose one end is maintained at 50. The other one, K A delta T. Now I am assuming inflow in the third rod also. So first temperature will be 0, final temperature will be T. So I should write 0 minus T. Depending on the direction in which you are writing the flow, you have to choose which temperature to take first and which temperature to take second. Divided by length is 2L. This is the net inflow and equated to 0. K and L will get cancelled. Okay. Now, if you observe, it's effectively the same equation that we got before. 400 minus 40, first bracket, plus second bracket 2 into 2, 4 into 50 minus t, that is 200 minus 40. This is what we had gotten before also. Third bracket is now minus t by 2. Earlier, we had equal to t by 2. T by 2 was on that side of the equation with a plus. Now it has come to this side of the equation with a minus. So it's the same equation. Then you will get the same answer, 70.59 degrees C. So it doesn't matter whether you write inflow is equal to outflow or you write net inflow is equal to 0, you're going to end up getting the same answer. But according to the direction in which you are assuming heat flow in a particular rod, you have to choose which temperature to take first minus which temperature to take second. Okay, right. Next, see, the equation that we are using, Ka delta T by L, it's valid when steady state is established. That too when conductivity and area of cross section are uniform throughout. Now it's quite possible that conductivity varies from place to place, or there are two rods of different conductivities attached. There are two rods of different areas of cross section attached. Okay, how to deal with such situations? Let us see. Consider something like this. Let's say there is one rod which is having some conductivity, some length, some area of cross section, and then consider another rod having different area, maybe different length, different conductivity also. Okay, they don't have to have any relation. Okay, it doesn't have to be straight also. Anyway, let's say across this combination, we maintain some temperature difference. Okay, left hand is at temperature T1, right hand is at temperature T2, T1 more than T2. You have to find out the effective rate of heat flow. First rod, let's say its conductivity is K1, area of cross section is A1, length is L1. Second rod, conductivity K2, area of cross section A2, length L2. As I said, they need not be related at all. But if there is a temperature difference, suppose T1 is more than T2, okay, there will definitely be transfer of heat happening. We have to find out the rate of heat flow. Okay. Once steady state is established, how much is the net rate of heat flow from one end to the other end? Can any of you give me an idea? How can we calculate the rate of heat flow in this case? Okay. Okay. So you are saying we'll assume some temperature where these two are connected, let's say T. And then how will you write the equation for heat flow? Like T is unknown, obviously. Steady state has been established, but we don't know this temperature. Now you can't say that temperature gradient will be same everywhere. Conductivities and areas of cross section are varying, no? So you can't say that this temperature difference divided by this length is equal to this temperature difference divided by this length. Okay, that will not be valid. So how to proceed? Like how to make use of this unknown temperature to write the equation?
So means earlier, when there is one rod, we used to equate the temperature, current, heat current.
Current. Good, good. Huh.
So here we will equate the common temperature.
Okay. Okay. I understand what you're saying. The way you put it is not correct, but I understand. So effectively, what we have to do is that only I told you that steady state has been established. Steady state established means what? Inflow is equal to outflow. That means heat current in the first rod should be equal to heat current in the second rod. And that will be equal to the overall heat current. That is what we want to find out. Okay. So you can write heat current in the first rod. This is one way to proceed. Heat current in the first rod will be K1, A1. I'm assuming current from left to right. So T1 minus T divided by L1 should be equal to K2, A2, T minus T2. In the second rod, I'm assuming it is to the right. So T minus T2 divided by L2. By solving this, you can get the temperature T first. Okay. After getting the temperature T, put it back in one of these equations, one of these expressions. You can put it here or you can put it here, you will get the heat current in both rods, which will be equal to the effective or the overall heat current. But this is a very lengthy procedure, and there are a lot of chances of making mistakes. Even if one calculation is done wrong, the entire thing will go wrong. But let's summarize this method once again. We have to write heat current in one rod and equate it to heat current in the other rod because steady state has been established. Using that, you can get the temperature T. Once you get temperature T, uh, you will again have to write heat current in any one of them. That will be the overall heat current. Okay, lengthy procedure. There is another better way to do it, or an easier way to do it. Now see, at steady state, we know that heat current dq by dt is equal to Ka delta T, the temperature difference between the 2 points, divided by the length. Fine. Heat flows from one point to another point whenever there is a temperature difference. And greater the temperature difference, from this equation itself you can tell, greater the temperature difference, greater will be the heat current. Okay. So it's like temperature difference drives heat current, and heat current is proportional to temperature difference, provided Ka and L are constant. Okay. Now, you must have come across something called Ohm's law in your 10th class. Can any one of you tell me what is Ohm's law? This is an electric current. This is related to electric current.
Sir, the amount of current flowing in a wire is directly proportional to the potential difference applied.
Good, good. Okay. The equation is written as delta V is equal to IR. Okay. Or for simplicity, we write it as V is equal to IR, but it's actually delta V is equal to IR. Potential difference across an electrical conductor is equal to current multiplied with the resistance. Okay. Not all conductors obey this, but some conductors do, and this is what we call as Ohm's law. So you can write I, electric current, is equal to 1 by R, inverse of resistance, multiplied with the potential difference. And from this equation, we can say that higher the potential difference, stronger will be the current across a given conductor. Okay. Potential difference drives electric current, just like temperature difference drives heat current. Now you can observe a similarity or an analogy between these two equations. In Ohm's law, you have electric current on the left hand side. In the law for conduction that we have discussed, we have heat current on the left hand side. You can call it as I. Okay. Right hand side, there is potential difference in Ohm's law. In the law for conduction, there is temperature difference. Potential difference drives electric current, temperature difference drives heat current. So they are analogous to each other. Okay. So heat current and electric current are analogous. Temperature difference and potential difference are analogous. Then whatever is between them should also be analogous. What is between them? In one expression, you have Ka by L. In Ohm's law, you have 1 by R. Therefore, inverse of resistance, okay, 1 by R is analogous to Ka by L. Or you invert both of them. Electrical resistance is analogous to L by Ka. Just a moment, let me verify this. Right. So R is electrical resistance. Fine. We'll learn that in detail in the chapter electrical current. When electrons flow through a conductor, they undergo collisions. Okay. The electrons are not allowed to freely move through a conductor. So that opposition to the flow of electrons is what we call as electrical resistance. Similarly, there is an opposition to the flow of heat that is called thermal resistance. So this term L by Ka that you see here is called thermal resistance of that conductor. Okay. Now, why are we discussing all this? Why are we deriving an analogy between heat current and electrical current? Because in electrical current, you must have learnt Laws of combination of resistances. Suppose there are two resistors connected in series, one next to another. One having resistance R1, the other having resistance R2. You can replace them with a single resistance, which is called effective resistance. Can one of you quickly tell me how much is the effective resistance of a series combination?
R1 plus R2 plus R2.
Okay. How many ever resistors are connected in series? You add all of them. You can replace that. I mean, you can consider that as the effective resistance. Then it becomes easier to solve the problem. Okay. You can do something similar in heat transfer also, conduction of heat also. So when there are two conductors given to you like this, two rods placed one next to another. So it's like they are in series. What were you asked to find out? Heat current. Okay. So we know the overall temperature difference and we want the overall heat current. But in between there are two conductors instead of one. So we were not able to write the equation. But what we can do is we can treat this as one thermal resistance. We can treat this as another thermal resistance and find out the effective resistance first. Then it's like there is only one conductor between the two temperatures. Okay. How do you write thermal resistance? We just discussed. Thermal resistance is L by Ka. So for the first conductor, the thermal resistance will be L1 by K1A1. For the second conductor, the thermal resistance will be L2 by K2A2. And these two conductors are placed next to each other. Heat has to flow through one of them and then through the other one. So they are in series. Okay. So how do you write effective thermal resistance? L1 by K1A1 plus L2 by K2A2. Once you know effective thermal resistance, you can directly write the heat current. How? Go back to Ohm's law. V is equal to IR. I is equal to V divided by R or delta V divided by R. Similarly, you can write heat current. Okay, the overall heat current in the combination of conductors is equal to, in place of potential difference, you'll have temperature difference. So T1 minus T2. You don't have to find out the junction temperature at all. Divided by, in place of R, you have to write thermal resistance. Just write the effective thermal resistance. It will be a lengthy equation, complicated equation, but you can write it directly like this. So this is another way to solve such problems when multiple conductors are connected. Similar ideas you can use for parallel connections also. So what is the idea here? You can treat a heat conductor or you can treat a thermal conductor similar to an electrical conductor. That is the idea. Electrical conductors offer electrical resistance, thermal conductors offer thermal resistance. And we drew an analogy between them. Thermal resistance of a conductor is given by L by Ka. So if multiple rods are connected, find out the resistance of each rod, then find out the resistance of the combination. You can tell the overall heat flow directly, overall rate of heat flow directly. Okay, that's the idea. Okay, we'll work more on this in the next class. And we will also discuss situations where conductivity varies continuously. Like in this example, we took two rods. One rod was uniform, another rod was uniform. Okay, so we took two uniform rods. It's also possible that in a given rod itself, area varies continuously or conductivity varies continuously. Okay, we'll deal with such situations in the next class. And these same ideas can be used in electric current also. Okay, fine. Thank you all. We'll continue in tomorrow's class. Yeah, tomorrow morning I'll be taking another class. Right.